Welcome to the Crypto for Crypto session. Our first talk is on the paper Craft, Composable Randomness Beacons and Output Independent Abort MPC from Time by Karsten Baum, Bernardo David, Raphael Dowsley, Ravi Kishore, Jesper Boos Nielsen, and Sabine Oshne. And Ravi Kishore is giving the talk.
Can you hear me? Yeah. Myself, Ravi Kishore. I'm going to talk about Craft, composable randomness beacons and output independent abort MPC from time. This is a joint work with my co-authors, Karsten, Bernardo, Raphael, Jesper, and Sabine. Agenda is as follows. I'll introduce you to the verifiable delay functions and time log puzzles. And I'll talk about TARDIS model of abstract composable time on which we build these protocols. And then I talk about probable sequential computations in UC setting. Based on this, I'll show you a couple of constructions for UC VDFs and publicly verifiable time log puzzles. And building on these constructions, I'll show you a couple of applications. One is MPC with output independent abort and efficient unbiasable randomness beacon. And I conclude with future works. Okay, so what is a VDF? VDF is a function and its output is generated only after performing a certain number of computational steps. And that means there is a delay is involved. And moreover, this VDF along with the output, it produces a proof. And this proof guarantees that to get the output, a certain number of computational steps have been performed. And moreover, with this proof, we can essentially check whether this computation, this output we got after performing these many computations is independent of the number of steps. So time log puzzle is another time-based primitive, which allows encrypting a message to the future. So to construct these primitives, we need a computational task that must be executed in sequential steps, taking at least some time. So in RSW96, first construction of TLP, and which is based on iterated squaring. Iterating squaring of elements from groups of unknown order. Let's see what it is exactly. Let's say you start with n, which is a product of two primes, as in RSA key generation. Now you pick an element, random element g from gn star. Suppose if you want to compute g to the power of 2 to the power of t, then you need to perform t sequential computations starting from g square, g to the power of 2 power 2, g to the power of 2 power 3, and so on, g to the power of 2 power t. So notice that suppose you know the order of the group, which is pi of n, then you can perform, you can compute g to the power of 2 power t much faster than t sequential computations, because g power 2 power t is nothing but g to the power of 2 power t mod pi of n. Okay, so under this assumption, how do you construct time log puzzle? So time log puzzle is nothing but g and then m times g to the power of 2 power t. Once you compute g to the power of 2 power t, then you can find the inverse and you multiply g to the power of 2 power t inverse with m times g to the power of 2 power t, and then you get back the message m. So that's the first construction. What are our contributions? I'll present UC treatment of verifiable delay functions. We give the definition and then matching construction. And same goes with PVTL, publicly verifiable time log puzzles as well. And then a couple of a few applications based on these primitives. That's one is UC MPC with output independent abort, and UC MPC with punishable output independent abort, and efficient randomness beacon protocol. Okay, so related works. A few works exist on modeling clock functionalities. In the first two works, model the wall clocks where parties and functionalities can ask for the current time. So whereas in the last work, which is we follow as well, where functionalities can ask only if a time unit has passed. And moreover, standalone time log puzzles and VDFs have been constructed, of course, which are not UC composable, and non-malleable time log puzzles too. Building on these time log puzzles, protocols exist for partial fairness for 2PC. However, like again, no composable guarantees for any of these except TARDIS work. TARDIS first introduced UCTLPs and presented an application 2PC with application for 2PC with output independent abort. Okay, so what is TARDIS model? In this TARDIS model, there is no global clock, but in place of global clock, we have a global ticker where functionalities can ask the global ticker whether a new tick has happened since the last tick. That means whether a time unit has passed or not. And then in response, global ticker responds with yes, a new tick has happened, or no, still in the same time unit. And whereas parties just observe the events from the functionalities. If suppose they get activated by the functionality, then before doing that, you just acknowledge just the global ticker that it got activated by the functionality. But in response, parties don't get any information about how many ticks has passed, whether the tick has passed or not. That's the TARDIS model for TARDIS model of abstract composable time. So now in this setting, I'll show you how we model the probable sequential computations. This functionality of PSC, which is PSC's probable sequential computations, this captures the notion of generic standalone trapdoor VDFs. So FPSC allows both computing and verifying sequential proofs. Okay, FPSC has 4 blocks: advanced state, trapdoor, solve, and verify. And then parties can ask, so present the from initial state ST0 and then solve it for T computational steps. It can ask for solve. And then when party or adversary asks for solve, that will be added to the list of puzzles being solved. And then in the say I-1 tick, parties are adversary asks for advanced tick. This it will be advanced only in the next tick. See, there is an epsilon parameter which we allow for adversary to get these. Like say, adversary may be a little powerful than the honest parties. So that is why if I is epsilon times t, that means by epsilon times t, adversary will get the yes after computing these t many steps. What will be the final state that gets? Yes, that is STT, and then get the proof. Whereas parties must wait until the tth sequential step happens, then only a party gets a final state STT and then proof pi. However, there is a block for trapdoor solve. Suppose they are somebody who's having trapdoor from the somebody who's having the trapdoor can starting from the ST0 in T steps directly gets the final state and then proof pi. So also this there is a verify interface as well. In the verify interface, when party asks for verify, gives the proof. This is the initial state. After T steps, this is the state STT, and then this is the proof. If you want to verify that, then suppose verification takes G of T time units. Then after G of T time units, this functionality outputs a bit B, where bit is yes, this is valid proof, or if B is 1, yes, this is valid proof. Otherwise, no, this is invalid. Okay, let's see our VDF construction based on this. So now you start with a random state ST0 from state space, and then you set your input as ST0, and then now you query the FPSC to solve this from starting state ST0. Then FPSC after T steps, it outputs STT and then pi. Okay. So once this is ready, you set your output as hash of final state and then proof which you got from FPSC. And then you set the proof of VDF as STT, and then the original proof you got from the FPSC. So how do we verify this? Now, once you have the output and then proof, you want to verify whether this is computed after certain number of steps. Then you pass your proof as STT and then pi. Now compute a hash, that is output prime, which is hash of T, STT and pi. Now you see you already have the original output, and then check what would be the hash you got, both are matching or not. If matching, then yes, that's the correct output. Otherwise, if you say that, okay. So that's the VDF construction. And then now let's see how to construct PVTLP. Here again some random state from state space. Now because it's the owner who is creating the time block puzzle, you simply send trapdoor solve ST0 to FPSC, and then you immediately get the final state and then proof. Now you compute the hash of all these, and then that is call it H1, and then you compute a tag which is XOR of this previous hash and this message. Now hash everything, you get the let's say call it H2, which acts as a commitment for these values. Now you output your TLP as ST0 and tag 1, tag 2. So now suppose somebody wants to solve this time block puzzle. So then like you have a now time block puzzle ST0, tag 1, tag 2. Now if you want to solve this, what do? You simply compute STT sequentially from ST0 and then get the proof, because FPSC outputs proof as well. Now and then you compute hash of as usual here, you compute hash of all these values, and then now extract the message M, which is tag 1 XOR with H1. Now you compute H2 because you already have now proof and then tag 1 and then message as well, and then see if it is matching with the tag 2. If it matches, then output message. Otherwise, it's an invalid time block puzzle. So how do you verify? Suppose somebody gives you the message and then proof contained in this message contained in this TLP. If you want to verify, then how do you do that? You pass your TLP ST0 tag 1, tag 2, and then because now you know the final state and then proof, you can directly get the you can directly find out the final state STT from proof pi, and then you follow the steps from 2 to 5 of the solve procedure. Yeah. So what are the applications? Now you know you have you know how to construct PVTLPs. So one application is output independent abort MPC. What is output independent abort MPC? The adversary, if adversary decide to abort, it must decide before learning the output of the MPC protocol. How do we do that? So you do MPC protocol as usual till the last round. But before sending the last message, what you do is you put that message, last message in the TLP. Now, honest parties, like every party now sends these outputs to the other parties. Now you expect to receive, if you are a honest party, you expect to receive the other party's TLP before your TLP is solved. If you don't receive, then you know that abort is detected. So that's the one application of TLP, and let's move on to efficient randomness beacons. Here also, protocol works as follows. All parties starts with some random number which they put in time block puzzle and then broadcast it. Now, say ith party's randomness is Ri, and then you broadcast it. And after broadcast delay, all the parties reveal their randomness and then trapdoor. If suppose some party don't reveal the randomness and then trapdoor, what you can do is, because the TLP you compute you'll be able to compute, you will be able to solve the time log puzzle. So once you solve the time log puzzle, so look for the valid ones, and then you XOR all the values. That is the output. So yeah, I mean that's the main idea. Suppose some party fails to open the TLP, but you know that TLP can be solved after certain time units. You just simply solve and then now XOR all the valid messages from the time log puzzles, and then you XOR, you get the you XOR all of this and you take it as output. Suppose some parties won't comply in opening their time log puzzles, then we can impose financial penalties. Yeah, so open questions, we can try for, we can look for UC compilers for fairness and efficient output independent abort for generic functionalities. Also, we can try to construct homomorphic UC TLPs and VDFs. Also, we can look for applications in crypto space. Yeah, thank you.
We have time for questions. I was wondering if you can comment a little bit more on the implications for rational MPC.
Yeah, so now, for example, like look at this protocol. After sending the TLP, you can expect immediately all the parties to open time log puzzles, like by providing the trapdoor. If suppose some parties are not providing, then you can impose financial penalties. So if computation is taking too much time, then you can adjust parameters accordingly. So if it is a rational adversary, then there is no incentive to cheat. So adversary behaves as honestly and then immediately tries to open the time log puzzle by providing the trapdoor.
Thanks. Any other questions? All right, well, let's thank the speaker. So next up, Daniel, is paper 24.
Sorry.
All right. So the next talk is on the paper Efficient and Universally Composable Single Secret Leader Election from Pairings by Dario Catalana, Dario Fiore, and Emanuele Giunta. And Emanuele will give the talk.
Does it work? Yeah, sounds better. So welcome everyone, I'm Emanuele Giunta, and today I will present this paper. It's a joint work with Professor Dario Catalano and Professor Dario Fiore from Catania and India Software Institute from Madrid. So today I will be talking about leader election protocols, and to give some motivation, the reason we study leader election protocol is because they are a way to achieve consensus in blockchain. So for instance, when we elect a leader in blockchain application, the leader is the one who is supposed to post, for instance, the next block in a chain and let everybody agree on the content of the chain at this moment. Now, since the leader has a very important role in keeping the protocol alive, it is important that when we elect a leader, we keep it secret in such a way that it is unfeasible for an adversary to maybe perform a DDoS attack on the leader and block the protocol execution. So for this reason, secret leader election protocol are actually deployed in practice, but they have a drawback. The fact that in many applications, they are just probabilistic secret leader election protocols. So this means that the protocol is divided in three phases. At first, there is a protocol to elect the leader. In practice, you can think of this as choosing a random input, and then user basically evaluates a VRF on these random inputs. Then there is a phase in which many potential leaders are elected. For instance, those who have evaluated the function, their own VRF, and got, for instance, a very low outputs, but they don't know yet they are the leader. And finally, revealing their own secret information, parties understand who is the leader. For instance, the one who got the lowest VRF value. And the protocol elected only one leader, of course, because there can only be at most one smallest value on expectation. So this is nice, and it's very efficient because it's non-interactive, but it creates some issues. For instance, the risk of creating forks, because if some party doesn't receive the output of some leader, some potential leader, maybe you can think the winner is someone else. And also it creates wasted effort, because if all those potential leaders have to create the next block, maybe they need to do some proof of work and they need to waste computation to do that. So for this reason, in 2020, Bonnet, Scandian, Hanzik, and Greco proposed a new primitive called single secret leader election, where there can only be at most one leader for each election, indeed. So this was proven to be harder to attack by Azuvi and Cappelletti in 2021. And the only disadvantage so far is that there is an inefficiency gap with the probabilistic leader election. Now, in this case, more interaction is usually required. So just to be more formal and precise, so in the case of single secret leader election, we tackle basically three properties that were defined in the first paper by Bonnet et al. And this property are essentially uniqueness, saying that for each election, there can be at most one winner. And notice that we cannot have precisely one winner because the adversary can win and say, and decide not to claim victory. So we can have at most one leader, but maybe none for some elections. We want to have fairness, meaning that all users have the same probability of winning one election. And finally, we want to have unpredictability, meaning that before the leader decides to reveal she won the election, there should be no way to guess who the leader is better than guessing at random. Unfortunately, the only issue with the definition proposed by Bonnet, Scandian, Hanzik, and Greco is that security may fail if we compose the protocol concurrently with itself. And actually, in the paper, we provide some situation in which this does happen. So this is a concrete threat. And for this reason, we propose a UC secure definition. So for those who are not familiar with the UC model, we essentially provide an ideal functionality which specifies how elections should be carried out. For instance, handling registrations for election. For instance, party can ask the functionality to do an election, and the functionality can privately tell one of those users that he won the election. And when this user wants to claim victory, this can communicate with the functionality and say, I want to claim victory. And the functionality convinces everyone that this is indeed the winner. And what we have to do is simply show that the real protocol behaves indistinguishably from the ideal protocol up to simulating missing messages. Prior to this work, and also after this work was published on ePrint, essentially we had only the game-based, secure construction in the first paper, and there were three of them. One based on indistinguishability obfuscation, and another one on threshold fully homomorphic encryption, which were mostly like of theoretical interest, although they have some nice feature. And the most practical one was a shuffling-based solution based on DDH. Which has as a main drawback the fact that essentially each user is associated to a ciphertext, and we need to permute this list. So we have a high on-chain cost. We need to keep this list on-chain for each election. Next, many other improvements to the on-chain, to the shuffle-based construction essentially were published with a paper last year in Pozzi, which improves this, achieving UC security and adaptive security. And there are other construction which, for instance, improved on, for instance, managed to distribute the shuffle. And finally, there is another construction that is based, I don't think it works. Okay, another construction that is based on MPC, which is has the advantage of having like very small on-chain complexity. So for verification, we don't need to put many things on chain, but it's very high on communication, on off-chain communication. So our construction, so the main feature that it achieves is that we use only well-studied and basic assumptions, and we achieve nice polylogarithmic on-chain efficiency. So this will be the main contribution of our work. So now I can just present a little like what are the technique we used. So the main building block we use to provide our construction is keyword search functional encryption and a slightly enhanced version of it. Keyword search functional encryption essentially is an encryption scheme in which there are functional secret keys that are associated to messages. In this case, SKY is labeled with message Y. And when we decrypt with secret key Y, we can learn if a ciphertext is encrypting Y or not. And that's the only thing we learn. We don't learn anything else about the message. So in the paper, actually, we do need a slightly enhanced version of this, which we call modular keyword search functional encryption. And instead of checking if X is equal to Y, we can actually check if X is equal to Y modulo N. So of course, the message X and Y needs to lie in some given set of integers, like in a given range. But those are like more technical details I won't go into. So at a high level, in order to present our protocol, I just need to specify two things. I need to specify how a user can register into the system and how elections are carried out. So at first, I will just focus on election, and then I will mention more, like I will say more about registration. But for now, we just need to know that our registration, we assume there is a subgroup of users who maybe have a secret sharing of the master secret key of the functional encryption scheme. And a registration time gives new user a secret key labeled with the identity that they have. So they have a secret key for the modular keyword search functional encryption scheme. And next, every time we want to perform an election, we begin by publicly selecting a random committee, hopefully small. And this random committee has the duty of computing a commitment to a ciphertext, to a challenge ciphertext. So this challenge ciphertext will be the one deciding the winner. So first, this committee create this commitment to a random challenge ciphertext. Then all the parties together threshold open this commitment and get the challenge ciphertext. And finally, only the user who is able to decrypt this message here is the one who won the election, and he proves it through a zero knowledge proof. Notice here that, by the way, the modular keyword search is important because this message here, M, identifying the winner, is essentially taken as the sum of several M1, MK, several shares, all lying in this range. So eventually this M will be lying between 0 and, if they're kappa user, kappa times N. So we need to do modular reduction here to check that the identity is equal to the message modulo N. So just to give also a bit intuition, like why this scheme is secure, we immediately have that this scheme satisfies uniqueness because for each M, reducing it modulo N, if the identities are from 0 to N-1, there can only be one secret key that decrypts this message. It is fair, it satisfies fairness because if there is at least one user, honest user in this committee, one of these MI is uniformly random in 0 N-1, and in particular, this M is uniform modulo N. And finally, it is unpredictable because other parties only learned that they didn't win the election, but they gain no information on who the winner really was. Okay, so just a little bit more detail on this. So again, the election phase begins by selecting a random committee, and this is done through a random beacon, which essentially gives random values and identifies a small subset. And this small subset again has to produce a commitment to a challenge ciphertext and encrypting like the sum of all these shares that they're randomly sampling. All of this like laying in the range from 0 to N-1. Okay. And so how do they do this? I need to go a little bit more on the detail of how the encryption scheme works. And this is, by the way, a modified version of encryption scheme by OTEQui from 2018. So we don't need to know much about the details, but just that the encryption comes from this expression. Those are like public key elements. And the issue is that the randomness used to encrypt, so everything is linear in the randomness used to encrypt besides for this term. So if everything were linear, the nice thing is that we could have each user in the committee select his own randomness. Then we multiply things together, and this would be a valid ciphertext. But because of this quadratic term, we cannot do this directly. So we might need more rounds, and this is problematic. So the way we avoid using more rounds of communication is through random oracles. So the idea is that we use the random oracle to sample two uniformly distributed group elements, and we interpret these two group elements as an encryption of a random message under El Gamal. or better, like a random commitment, random Elgamal commitment. That is the orange element in here. And then we use linearity of Elgamal to build the remaining parts of the ciphertext, which now only depends linearly on the secrets. That is the message and the randomness as used for the encryption. So now we just can compute everything in one round by having first the random oracle compute this orange part, and then user in the committee producing their own share, and finally multiplying things together. So to conclude the election, we just need to instantiate the threshold decryption. I didn't mention maybe, but we assume that this is a random Elgamal commitment under secret key Z. So we assume there is like G1 and ZG1 publicly available to every user, and also that every user has a share of Z. So user can threshold decrypt, and this is just the standard Elgamal threshold decryption. There is nothing new. And finally, to claim victory, the winner simply provides a zero-knowledge proof that he knows a secret key decrypting the challenge ciphertext. And this can be done easily with Sigma protocol, like very efficiently Sigma protocol. So finally, I just need to explain how the registration works. And the idea is essentially the same. So we assume that at setup time, there is a committee, this time probably larger committee of user, who has a secret sharing of the master public key for the encryption scheme, and for the secret Z, that was the secret key for the Elgamal commitment scheme. Okay, so this can be simply done by having each user sampling random WI and ZI, and then implicitly defining W and Z as the sum of all these shares. So given this, the secret key in our schema is essentially this shape. And we again have the same problem. We have this randomness R that it's fresh for each secret key. In this case, okay, we just have it. But here we have quadratic dependency with the randomness and the master secret key. So in theory, we would need more round of interaction to compute a sharing of R times W. But again, we can use the same trick of the random oracle by generating these elements randomly for all the user in the committee. And finally, having each member of the committee give to the user like WI times all these things, and then multiply all these elements together in order to get the correct secret key. Okay, so to conclude, we have, okay, so we did compare our work essentially with the shuffle-based solution by Bonnet, Scandiner, Hansik, and Greco. And in particular, we observed that, okay, so for each column, as here, we assume that we perform an election, and between every two elections, there are 10, 20, and 50 registrations, just to provide, I mean, just to have a way to compare both registration and election at the same time. And we observed that in our case, the setup cost is a little bit, is of course more than the shuffle-based solution, because we need to instantiate the verifiable secret sharing at first, which is a bit high in communication. But then the fact that our registration is very efficient, the committee simply need to send a constant number of group elements to the new user. The cost of the scheme is eventually better than the shuffle-based solution, where you need to shuffle the whole list every time there is a new user. And this is a problem, by the way, that does affect all the shuffle-based construction that came afterwards. So the efficiency in those cases are comparable with the first construction. And even for on-chain costs, our scheme is even better than the square root of n shuffle, where you only shuffle a subset. So you have even less anonymity in that case, but still like very high on-chain complexity for the previous constructions. So to sum up, what I present today is a practical and secure SSLE scheme that achieve polylogarithmic on-chain complexity and only relies on standard pairing assumptions. So there are still problems and ways to improve this protocol. And for instance, one of those questions is, can we reduce the setup cost? Like, do we need to use the verifiable secret sharing, or can we use different techniques? And finally, if it's possible to achieve adaptive security in our setting. For instance, the reason why we don't achieve adaptive security is that we rely on committees, and if those committees are fully corrupted adaptively, then the adversary completely breaks the system. So we can only prove security against static corruptions. So that's it. Thanks for your attention, and I'm glad to take questions.
Thank you for the talk. We have a few minutes for questions.
So I didn't get how to make sure that the N is correct in the encrypted messages.
Okay, I missed. I mean, I didn't mention like how we ensure that all these ciphertexts are correctly generated. But in fact, the small n is the number of registered users at the moment, and this is a public information. And in fact, all user in the committee that produces these partial ciphertexts that are later aggregated need to attach a zero-knowledge proof of that. And n is part of these statements that the ciphertexts are correctly generated. So it has to be the number of registered users at the moment. Thanks for the question.
I actually have a quick question. Oh, so
Maybe there was one in the back. Okay.
For the zero knowledge proof, do you use Sigma protocol or like customized protocol based on pairings?
Okay. So essentially, we use the fact you mean the zero knowledge proof for the for proving like that I can decrypt the challenge ciphertext. Okay. So we essentially use the fact that our encryption scheme and especially the decryption procedure is essentially linear. So we can essentially adapt like known techniques like this grammar version of Sigma protocol for linear statements. So essentially, it's basically a Schnorr proof, but for a slightly modified statement. And also, like since the ciphertext has only a constant amount of group elements, the proof also has like 5 group elements in total, if I'm not wrong. Thanks for the question.
I'm going to ask my question. Okay. So this is a beautiful construction, and you really kind of, it looks like SXDH is doing a lot of heavy lifting there. Mm-hmm. So I was wondering, what are your thoughts on achieving the same asymptotics, but from other assumptions?
So I think that without pairing, it's probably hard because, I mean, we need pairings to have functional encryption there. And without it, I'm not aware if there are like keyword search functional encryption for weaker assumptions. I believe it could be possible from lattices, but I don't know if efficiency-wise would be better or not. But that's definitely an interesting question. Thanks.
Thanks. All right, other questions? All right, so let's thank the speaker. So, so Daniel, the next paper is paper 37.
Were we turning it off? Yeah.
All right. So, so our next paper is a simple, fast, efficient, and tightly secure, non-malleable, non-interactive timed commitments by Peter Chwoika and Tibor Jager, and Peter will give the talk.
Okay, thank you for the introduction. Can you hear me? Yes, okay. So hi everyone, I'm Peter, and I'm going to talk about simple, fast, efficient, and tightly secure, non-malleable, non-interactive timed commitments, which is joint work with Tibor Jager. And let me start with motivation example. Imagine that you have a set of bidders who wants to participate in sealed bid auction. And the first thing they do, they commit with standard commitment scheme to their bids. And they publicly made these commitments to available everyone. And at some point of time, they reveal their bids. But now assume that one of the bidders claims, oh, I lost my randomness, I'm not able to open the commitment. And he claims that his bid is the highest, which is interesting for the seller because he wants to sell the item for the highest price. And now the question is, can we resolve this issue? And one way how to resolve this is use so-called timed commitment. And timed commitment has additional feature which we call force decommitment. And this feature allows to open the commitment at a specified point of time automatically without the intervention of another users. So what we require from such a timed commitment are following properties. The first one is called public verifiability of the commitments. We want to be sure that the commitments are correctly generated. And also we want to be especially sure that they can be really force decommitted. Then non-interactivity for practical reasons. We want to be that they are non-malleable. We don't want to allow users to create their commitments based on the time commitments of another users. Then some kind of homomorphic properties can be interesting because usually this forced decommitment requires to execute some sequential computation, which can be expensive. And now imagine that several users reject to open their commitments. In the case that we are interested only on some evaluation on the messages which are hidden in these commitments, we can homomorphically combine the time commitments and then force decommit only a resulting time commitment. And then we also introduce this new property which we call public verifiability of the force decommitment. And this allows to outsource the computation of the force decommitment to untrusted server. And he can prove us that he executed the force decommitment correctly. Okay, this has found several interesting applications like achieving unbiased e-voting or fairness in multi-party computation protocols like fair coin flipping and several others. Let's start to be a little bit more formal. Non-interactive time commitments were introduced by Katz et al. And it is a couple of algorithms. So we have a pigeon algorithm, which takes us into the security parameter and time parameter and outputs a CRS. Then we have committing algorithm, which commits to the message and produces commitments and also committing and decommitting proof. Then verify algorithm that checks that the commitment is correctly generated. Decommitment verify algorithm, just think about it as a standard opening algorithm for the commitment. And then we have this special force decommitment algorithm, which allows to open the commitment without any secret information. And the requirement is that the runtime of the algorithm is roughly T. As I mentioned, we introduced this new property called public verifiability of force decommitment. And in that case, the force decommitment additionally outputs also additional algorithm force decommitment verify, we check that the force decommitment was executed correctly. And then Taragayan et al. Also introduced these homomorphic properties where there is an evaluation algorithm which works in the following way. It takes us into the CRS, circuit and set of time commitments, output another time commitment, and then we can run force decommitment algorithm and obtain evaluation of the circuit on the messages which were hidden in the time commitments. There are actually several security properties which are required from such a time commitment. But in this talk, we are going to focus only on one, which is called IND-CCA security. And this property is actually very similar to IND-CCA security of public key encryption. And it works in the following way. Adversary A consists of two machines, A0, A1. And then the challenger runs pigeon algorithm to obtain CRS. It sends CRS to the A0. A0 can ask decommitment queries, but we are going to answer decommitment queries only for commitments which are correctly generated. And the requirement is that we answer them using force decommitment algorithm. So at this point, I want to mention that if we want to achieve tight security proof, in the proof, there must be another way how to answer these decommitment queries, because the runtime of this algorithm is roughly T and it might be expensive. Then A0 provides a challenge messages. Challenger randomly sample a bit, commit to the message MB, compute the commitment, provides a challenge commitment to the adversary A1. A1 again can ask these decommitment queries. Again, we are going to answer only correctly generated commitments, and it must be also different from the challenge commitment. And then adversary A1 outputs bit B prime. And the requirement is that the runtime of the adversary A1 is less than T, because otherwise A1 can run this force decommitment algorithm and he would be able to see what is inside of the commitment. And then the output of the experiment is defined as the truth value of the expression B is equal B prime, and advantage is defined as a probability that experiment outputs 1 minus 1/2. Okay, so I told you that this security notion is very similar to IND-CCA security notion of the public key encryption. And also we need this public verifiability of the commitments. So therefore, the idea is to start a publicly verifiable public key encryption scheme. And the candidate is, of course, now Young paradigm, where you can encrypt the message twice using two independent keys, using CPA secure public key encryption scheme, and then prove using one-time simulation sum NISIC that that both encryption contain the same message. Okay. And we want to have, however, efficient construction that means also efficient NISIC. So the base would be some Sigma protocol, and we know that the Sigma protocol exists for algebraic languages. And therefore, the challenge is to find a replacement to substitute this public key encryption scheme. Okay, so the candidate for such a substitution is actually homomorphic time lock puzzle of Malavolta et al., which consists of 4 algorithms: setup, gen, solve, and evaluation algorithm. And this evaluation algorithm works as expected. And now notice if I just rename the algorithms as pgen, com, and force decommitment, then I have a timed commitment. But this time commitment has very weak or weaker security notion, and it's very similar to CPA security notion. Okay, so this is the candidate. And Malavolta et al. Show how to build this primitive from the strong sequential squaring assumption, which is the following assumption. Adversary A again consists of the 2 machines, A0, A1. And challenger runs gen mod algorithm, produces 2 large primes, P and Q, and is the product of the primes, and G is some generator. We provide NT and G to the adversary A0. And then challenger randomly sample X from the group of J of N, which is the subgroup of Z and star of elements with Jacobi symbol 1. Y0 is computed as X to the 2 to the T mod N, and Y1 is the element of J of N. And I define it as 2 experiments. So in one experiment, we provide X and Y0. In second experiment, X and Y1. A1 output B, bit B prime, and the runtime should be less than T of the algorithm A1. And the advantage is defined as a probability that adversary A outputs 1 in experiment 0 minus probability that adversary A outputs 1 in experiment 1. Okay, so in their paper, actually, they show linearly homomorphic and also multiplicatively homomorphic construction. In this talk, I'm going to talk about only linearly homomorphic construction of time lock puzzle. So in pgen, they run this gen mod algorithm. Then they compute this Euler function phi of n, which is p minus 1 times q minus 1. And then they compute the special value t as a 2 to the t mod phi of n divided by 2. And this is the order of the group of j of n, and h as g to the t mod n, and CRS is then np, g, and h. And now the commitment is something very similar to PyA-like encryption, where we randomly sample R from some interval and compute C0 as G to the R mod N, and C1 is very similar to PyA, H to the R times N times 1 plus N to the power of M mod N squared. And now notice we can force decommit it without any secret information. We compute the value Y as C0 to the power of 2 to the T mod N. And this can be computed by repeated squaring, and it takes T steps of the repeated squaring. Therefore, we say it has runtime roughly T. And the message can be recomputed as C1 times inverse of Y to the power of N mod N squared minus 1 divided by N. And now notice we have also PyA-like homomorphism. It is sufficient to multiply separately C0 parts of the commitments and C1 parts of the commitments. And additionally, we can also define standard opening algorithm. If you give me a message and randomness, I recompute the commitment from the scratch and just check if it matched the claimed commitment. And this was shown to be kind of CPA secure based on strong sequential squaring, decisional composite residuosity, and decisional Diffie-Hellman assumption. So our first attempt how to obtain this CCA security is just use combine 2 independent homomorphic time lock puzzles which were produced using 2 independent keys. Okay, and on this slide I also wrote 2 independent modulus N1 and 2. But in reality, if we want to just use standard Sigma protocol, then N1 is equal to N2, and from now on I assume that this holds. Okay, and now let's look what will happen in the security proof. So I told you that in the experiment, there is this requirement. We have to answer these decommitment queries using forced decommitment algorithm. And in order to obtain time security proof, there must be another way. So let's say we use key T1, and this is indistinguishable based on the soundness of the NISIC. Then we can start to simulate the proof. Okay, here we rely on the zero knowledge property of the NISIC. And now we can try to replace the message in the second homomorphic type block puzzle with the random message. But now what happens? This key T1 has this special form, 2 to the T mod order of the group. And in order to compute this key, we need to know the order of the group, and essentially we need to know the factorization of n. But at the same time, we need to reduce the security of homomorphic time puzzle. And especially we need to reduce to the strong sequential squaring assumption. And this assumption does not hold if we know the factorization of n. So we are a little bit stuck with this approach. And there is a simple observation that from this homomorphic time lock puzzle, we can just get simply homomorphic, linearly homomorphic public key encryption scheme. If we sample the key T uniformly at random from some interval, and then I just simply rename the algorithms and I have standard public key encryption scheme, which is CPA secure based on decisional composite residuosity and decisional Diffie-Hellman assumption. Okay, so what is our second attempt is to combine homomorphic time lock puzzle with this encryption scheme. And they were produced using independent keys. Okay, but now what happens in the proof that at some point of the time, I again have to use this key T, which is this special form, and for which I need to know the factorization of n, and I will have to reduce to the DCR assumption. And now the problem is the DCR assumption does not hold if I know the factorization of n. So we can fix this issue simply by what we call triple Navier-Young. And triple Navier-Young is you can encrypt the message twice using 2 independent keys, and the third time you commit using this homomorphic time lock puzzle, because you still want to have this feature of forced decommitment. And why this works? So in the security proof, you can always answer the decommitment queries either using key K1 and change the message. Change the message in the homomorphic time lock puzzle and second public key encryption scheme with random message. Or you can answer them using key K2 and then change the message in the first public key encryption scheme with the random message. And you never have to rely on this special key T, for which you needed to know the factorization of n. Yeah, so the security proof simply works. And this is essentially our construction, but we can do a little bit better. We can use the technique of the Biagioni et al. And instead of having 3 independent keys and 3 independent commitments, we can generate just one generator G and produce H1, H2, H3 with respect to this generator G. And then we can commit with using shared randomness. So we compute G to the R, and then we compute these 3 pi-like commitments using the same randomness R. Okay. So instead of 6 elements, we will have 4 elements. And therefore, we need one-time simulation sound NISIC for the language, which shows that C0, C1, C2, C3 is correctly generated commitment and contains only one message and randomness. And in our paper, we show how to build a Sigma protocol for this NISIC, and we show how to obtain either NISIC in random oracle model or in standard model using this collision intractable hash function. Okay. So to just point out to the important things, okay, in PGen, we randomly sample these 2 keys, K1, K2, from some interval, and then we have this special key, which is computed as 2 to the T mod order of the group. And if we have a NISIC in standard model, then we have also the setup of the NISIC, CRS of the NISIC. And then we commit, as was explained on the previous slide, with the shared randomness. And we prove that the commitment is correctly generated. And the randomness R is actually just standard opening of the commitment. Okay. And in our paper, we also show how to implement all other algorithms efficiently. So to conclude, in our paper, you will find 4 constructions. 2 constructions are linearly homomorphic, 2 constructions are multiplicatively homomorphic. And always one is in random oracle model and one is in standard model. And compared to the previous works, we either achieve efficient committing time, tight security proof, some novel properties, smaller size of the commitments, or that the constructions are standard model, because often they are in a random oracle model. Okay, if you are interested in the paper, you can just find it on the ePrint, or you can even contact me via my email. Thank you for your attention. If you have any question, you are welcome to ask.
We have time for questions? Questions? So I have a question about applications of this type of commitment.
Yes. So as I told you, like very often you want to use it for achieving this fairness in the multi-party computation protocols like fair coin flipping. So you like, for example, in this coin flipping protocol, like it can happen that at some point the participants see their messages which they are sending in the protocol, or when they are opening the commitments and one would reject to open, then the protocol fails. Yes, but because they commit, for example, with this time protocol, they can still open also the commitments of the other users and the protocol will continue.
How is it different from verifiable delay functions?
I mean, verifiable delay function, you are really not committing to the value, yes? It's just the output of the, this verifiable delay function is good for achieving this unbiased beacon, yes? But for example, it wouldn't be good for achieving unbiased e-voting.
Right,
yes?
okay.
It would be not enough. Yeah.
I guess my bigger question is the relationship between this result and the one we just heard in our,
Yeah.
craft.
Okay.
Yeah, but that's.
Yeah, so yeah, the construction is UC secure. Yes, also they have to also rely on the random oracle model. And if it is UC secure, I think it means it's automatically non-malleable, but they don't have, for example, these homomorphic properties. Yes.
Oh.
Okay, thank you for your talk. I want to ask, what assumptions do the first 3 works rely on?
Okay, okay. It's this sequential squaring assumption is in all of them, I think, and the second one is relying on generic NISICs. So therefore, like they are relying on snarks actually.
Snarks.
Yes. And they are the first 2 are, or all of them are in the random oracle model, I think. Yes. So they are also relying on the oracle.
Okay, thanks.
Yeah. Welcome.
So the next paper is paper 83. All right, so our next paper is Certifying Giant Non-Primes by Charlotte Hoffman, Pavel Hubachek, Chetan Kamath, and Krzysztof Pieczuk. And Charlotte will give the talk.
Okay, thanks for the introduction. So I hope you're not too disappointed that this is not going to be a talk about crypto for crypto, but we're going to see an application of crypto in computational number theory. Namely, we're going to look at prime numbers. So prime numbers have always been of interest, not only in number theory, but also just in the general public. So for example, there are those large-scale projects that are dedicated to searching giant prime numbers. They are called GIMS and prime grid. And when I say giant, I really mean giant. So the largest prime number that has been found by PrimeGrid consists of more than 9 million decimal digits. To find those numbers, the projects perform expensive primality tests for numbers of special form, for example, Proth numbers or Mersenne numbers. And to prevent cheating and computation errors, until recently, they have done this via double checking. So two different parties check the same number, no matter if the result was prime or not prime. But of course, we as cryptographers, we can ask ourselves if we can replace this expensive double checking with cryptographic proofs. And in our work, we show that this is possible for some specific cases. Namely, we're going to look at Proth numbers. So Proth numbers are numbers of this form, k times 2 to the n plus 1, where k is odd and it is strictly less than 2 to the n. And for numbers of this form, there exists a well-known primality test called Proth's theorem. So this says that for any x, which is a quadratic non-residue modulo n, we have that n is prime if and only if the following holds. We take x, we raise it to the power k times 2 to the n minus 1, and then we check if the result is -1 modulo n. If the result is -1, we know that the number is prime. If the result is not -1, we know that the number is composite. But notice that even if we now know that the number is composite, we do not get a divisor of the number. So we don't have a proof that this was actually the correct result. But if we look at the primality test, we see that this is this big exponentiation. So and in cryptography, we have a tool to certify the result of some big exponentiations, and those are called proofs of exponentiation. So there we have a prover and a verifier, and the prover claims that the result of some big exponentiation is equal to y in some group G. And to prove this, the prover can send a POE, so proof of exponentiation. Those POEs are usually only interesting in hidden order groups, because if you know the group order, then the verifier does not need any help from the prover. It can just reduce the exponent modulo the group order and then raise x to that power. And it's usually efficient, and it can just check if the result is true or not. But if the group order is hidden, then we don't know of a significantly faster way to compute the result than to perform T sequential exponentiations. So that's what the prover does. Then it sends a proof of exponentiation for which the cost of computing and verifying it is much less than T. So the verifier does not need to work as hard. Okay, so this looks promising. Now, can we use this for our primality tests? So can we use POEs for primality certificates or non-primality certificates? Yeah, again, here you see the primality test. It's this big exponentiation. And in fact, GIMS and PrimeGrid have already discovered this connection, and they have deployed PHX POE to certify primality tests. But there's a problem here. So as I just said, PHX POE was constructed for hidden order groups. And now we're working in the group Z modulo n. So if n is a prime number, then we know the group order. It's just n minus 1. So notice that this does not speed up this computation because the group order is still larger than the exponent. So we cannot reduce the exponent anymore. However, PHX protocol is unfortunately not sound in those groups. And in fact, there even is an attack. So for any Proth prime number, the prover can come up with a false proof, convincing the verifier that the number is composite, even though it's not. Notice that there are other POEs in the literature. There are also statistically sound POEs that work in any group. However, they are more complex. And because we are working with such huge prime numbers here, we really cannot afford to use a POE that's much more complex than PHX POE. Right, so in our work, we take care of this problem. So our contribution is we construct a statistically sound certificate of non-primality for Proth numbers that reduces the complexity of double checking from n multiplications to O of lambda times log n, where lambda is a statistical security parameter. And it increases the complexity of the currently deployed protocol, which is not cryptographically sound, only by a multiplicative factor of 2. Okay, again, note, so this is a certificate of non-primality. However, in practice, most of the numbers are not prime. And so with this certificate, we cover almost all of the cases. Okay, now how do we achieve that? The rest of the talk, we're first going to look at PHX PoE. Then I will show you the attack and proth number groups. And then finally, we'll see our protocol. But first, I want to remind you of the definition of interactive protocols. So again, we have the prover and the verifier, and they both get as input some statement X, and then the prover also gets a witness or just more computing power than the verifier. Then they send messages back and forth until in the end, the verifier outputs accept or reject. And we say that this protocol is sound if whenever the statement is false, then the verifier rejects with high probability, no matter what the malicious prover does. And we say that it's complete if whenever the statement is correct and P is honest, then the verifier accepts with high probability. In this talk, all of the protocols will be trivially complete, so we're just going to discuss soundness. Okay, so let's take a look at PHX PoE. Here, the statement to be proven is that X to the 2 to the T equals Y in some group. To prove this, the first message of the prover is this element G1, which we also call midpoint, because it's the result of the exponentiation X to the 2 to the T over 2. Notice that by sending this element, the prover implicitly splits up the first claim into two smaller claims. So one of them is that this G1 is actually the correct result of this exponentiation with 2 to the T over 2. And the other claim is that if you take the midpoint and raise this one to 2 to the T over 2, you should get back Y, which is the result of the initial claim. Okay, good. So now we've made some progress. We've reduced the exponent from 2 to the T to 2 to the T over 2, but we now have two statements instead of one. And so to take care of this, the verifier now sends a random coin R, and the prover and verifier fold those two statements back together into one, like this. So we obtain this equation down here by taking the first statement, raising it to the power R, and then multiplying this with the second statement. Okay, and then now we've really made progress. So we've reduced the exponent from 2 to the T to 2 to the T over 2. And now the prover, again, just needs to prove one statement. So we can recurse. The prover again sends the midpoint. And we do this for log T many rounds until in the end, the verifier just needs to check the result of this one squaring. And then it can output accept or reject. Notice that all the messages the verifier sends are just public random coins. So this protocol can also be made non-interactive using fiat-Shamir. Now, what you can see is that if the prover here starts off with the wrong statement in the beginning, then no matter what it sends in the first message, at least one of the new statements will also be incorrect. However, for soundness to hold, we need that also after the folding step, we still have a wrong statement here. So that in the end, the verifier notices that there's something fishy. So PHX proves that this holds in certain groups, but unfortunately, it does not hold in proth number groups. And now we're going to see the attack. So let's assume that we have a prime number, a proth prime n. So the correct result of the primality test is -1. However, we have a malicious prover that claims that the result is actually minus alpha for some other element alpha. Now, there are different messages that the prover can send in the first round. It's not really important to us how it looks like, but as we just said, we still have that one of the new statements is still incorrect, and this bad element alpha is still in there somehow. Then the verifier sends a random coin, and then we fold the two statements back together into one. So we take them, we raise the first one to the power R, and then we multiply it with the second statement. But this might be a problem, right? Now we have this bad element here, and we raise it to some random number. So we might actually be unlucky and have that alpha raised to that a random number equals 1 modulo n. And then this means that the bad element vanishes from the claim. We have a correct claim, and the prover can be honest in the rest of the execution, and the verifier will never notice that there was something wrong in the beginning. Now, what's the probability of this event happening? Well, that depends on the order of alpha. So if we say that alpha is an element of order d, then the probability that alpha raised to a random number equals 1 modulo n is just 1 over d. And so we have that the probability that the verifier accepts that n is composite, even though it's prime, is at least 1 over d. I forgot to say that this attack was first shown in the context of VDFs by Bonebens and Fish. Okay, good. So this is a problem, but in our setting, we can take care of it. So let's see, for our work, we first make some observations. So here I'm reminding you again of Prost's theorem, and now we're in the setting where we have a prover that claims the number is composite and the result is minus alpha. So the first observation we make is that in this case, the verifier only needs to exclude that the correct result is -1. So we don't care if the prover cheats a little bit and claims that the result is minus alpha, even though it's 7 or it's 13 or whatever, because in all of those cases, we would have that the number is composite, and that's all the information that we want. We just need to rule out that it is actually prime. Then we have seen that the success probability of the attack depends on the order of alpha. But if we assume that we have a malicious prover, then n is prime, and then we know the group order. It's just n-1. And we know that the order of alpha, because it's an element of the group, divides this order. So then we know that alpha divides k times 2 to the n. And we can use this information to check if the order of alpha is too small. Okay, so here we're in a lucky situation, which is very different from the usual settings when you use VDF. We're assuming that if we have a malicious prover, then we have a prime number. And so by assuming we have a prime number, this gives us much more structure that we can use to construct a sound protocol. And this is how the protocol looks like. So again, this is a non-primality certificate. This is Prost's theorem again. And now we have a prover that claims it has a number that is composite. So the result of the primality test is minus mu for some mu that is not equal to 1. And now what the verifier does is it performs checks on the order of mu, and then depending on the outcome, the protocol looks differently. So let's first assume that the verifier has raised this element mu to the power k and has already gotten 1. So that means the order of mu divides k, so it's odd and it is small. This isn't for the verifier a very lucky case, because then again, it doesn't need any help from the prover to check if the result is true. So I don't want to go into detail what the verifier does, but it performs some number theoretic tricks, and then it can just output accept or reject soundly without ever seeing a message from the prover. The second case is that the order is large enough. So the verifier has taken the element mu, raised it to the power k, and then 2 to the lambda times log n, where lambda is some statistical security parameter, and the result is not 1. Again, recall that if we have a malicious prover, the order of mu divides k times 2 to the n, and now we've raised it to k times a sufficiently large power of 2. We didn't get 1, and so this means the order of mu is very, very large. So the success probability of the attack that we have seen is negligible. And so in this case, the prover can just send PHX POE without anything else, and then the verifier can soundly output accept or reject. And the last case is that the order is even, but it's not big enough. So we're performing this check, raise mu to the power k times 2 to the lambda log n, we got the result 1. So in this case, we're going to use a trick that's similar to the one we used in a paper from last year at Crypto. So we let the prover stop a little bit earlier. The prover should not perform the entire exponentiation, but it should stop at 2 to the n minus 1 minus lambda times log n, and output the result y, and also prove that y is the correct claim. And then the verifier performs the final exponentiation itself. So it takes this y, raises it to the power 2 times lambda times log n, and then checks if the result is really minus mu, as the prover claimed. Again, I don't want to go into detail of why this is sound, but the idea is that by performing this final exponentiation itself, the verifier somehow weeds out potential bad elements that the prover used to cheat with. And so also this case is statistically sound, and the verifier outputs accept or reject. And that's the protocol. Now we've covered all of the cases. So to sum up, we construct a non-primality certificate for prof numbers with the following efficiency properties. So compared to PHX POE in prof number groups, it's only slightly more complex, but our protocol is statistically sound, and PHX POE didn't give us any cryptographic soundness. And compared to double checking, we've reduced the complexity of verifying from n multiplications to O of lambda times log n. So in practice, that means we've reduced the work from weeks to hours. One interesting open problem is to also construct a cryptographically sound certificate of primality. As I said before, most numbers are composite, so our certificate already covers a lot of the cases, but of course it would be nice to cover all of them. And another open question is to construct similar certificates of non-primality for other types of whole numbers, such as Mersenne numbers, which are of the form 2 to the n minus 1. And that's it. Now I'm happy to take questions.
Thanks. We have plenty of time for questions. So my question was, why are Proth primes interesting? Why is there, why was there so much interest in this? And why is it interesting that they're non-primes?
Right. So Proth primes are interesting for the community because we have such a nice primality test, which is deterministic, right? So yeah, that's why they're testing a lot of Proth numbers. And then yeah, of course, you want to make sure that you don't miss a prime number. So when you work with such giant numbers, so you want proof for both cases. You want to be sure when you found a prime number, you want to be sure that it's prime. But also when someone claims, no, this number is composite, then you also want to be sure it's actually composite and you have not missed a big prime number. Yeah.
Well, let's thank Charlotte and let's.
Thank you.
Wait, I'm going to introduce you first.
Oh.
Hi. So the last paper in the session is Transparent Batchable Time Lock Puzzles and Applications to Byzantine Consensus by Shravan Srinivasan, Julian Loss, Julia Malavolta, Kartik Nayak, Babis Papamantu, and Sri Tyagarajan. And Shravan will give the talk.
Hi, I'm Shravan Srinivasan. Thank you for the introduction. I'm going to repeat it. This is a joint work with Julian Loss, Julia Malavolta, Kartik Nayak, Babis Papapantu, and Sri Aravindakrishnan Tyagarajan. So our work is on building transparent batchable time lock puzzles that has applications in Byzantine consensus. Thanks to the speakers before me, they pretty much gave all the setup and examples, which I'm going to go over in this talk. But yeah, here is it one more time. So time lock puzzle is a cryptographic primitive that lets Alice encrypt a message into the future. Say Alice wants to send a message M to Bob. Alice puts this in a time lock puzzle and gives it to Bob. Bob will be unable to open this time lock puzzle before time t. Two key properties which we want from the time lock puzzles are, first, it should be easy for Alice to generate a time lock puzzle. And even if Bob employs parallel strategies, Bob should not be able to open the time lock puzzle anytime before t. Time lock puzzles have found applications in timed commitments, auctions, blockchains, and many more applications continue to emerge. Unfortunately, existing time lock puzzles have a key drawback. First, it does not scale with multiple users. Say in a setting like auction, where you have to open up multiple time lock puzzles to figure out who the winner is, then with traditional time lock puzzles, you are stuck with opening one puzzle at a time. However, batchable time lock puzzles are just new primitives introduced by Malavolta Tyagarajan. In this setting, in these constructions, you can combine many individual time lock puzzles into a single batched puzzle, and you can open up the batched puzzle for the price of one. Yeah, as mentioned by the other speakers before, they also support homomorphic properties where you can in fact perform computations inside the batched puzzle. So yeah, the batch time lock puzzle is the focus of this work, and there are two known batch time lock puzzle constructions. One is based on the RSA setting, and the other one is based on class groups. RSA-based setting, RSA-based construction does require a trusted setup, On the other hand, class groups based construction does not require it. However, both of these constructions suffer two drawbacks. First one is these constructions require an a priori bound on the batch size, meaning someone, even before they generate a puzzle, they should know the total number of puzzles that could be bashed in this setting, and which is a drawback because you can't do unbounded batching. Another drawback is the puzzle sizes in these settings are linear in the number of people in the batch size. So you're stuck with large puzzle sizes in these constructions. So we ask in this work, can you build a batchable time lock puzzle that has transparent setup, can support unbounded batching, and has puzzle size independent of the batch size? Yeah, so why do we care about a time lock puzzle with these properties? So the first crucial, these time lock puzzles have applications in the context of decentralized setting, especially in payments, consensus, and MEV prevention, and so on. So considered in a permissionless setting, these properties are off the bat useful. So first, we don't know the number of nodes that are there in the system. And it's also impractical to rely on a trusted setup. Moreover, you are stuck with large puzzle sizes in the previous constructions, and that increases the communication overhead as well. So our contributions are as follows. So we introduce a new time lock puzzle, which is batchable, has transparent setup, and can do unbounded matching, and has compact puzzle size. However, we use indistinguishability obfuscation. So this makes it a feasibility result, and we see that there are no fundamental barriers in achieving a construction like this, and we leave the task of coming up with an efficient construction to future work. So these time lock puzzles are useful in consensus, and especially they solve two long-standing open problems. First one is in the context of permissionless setting. So in this setting, in the setting, it's called as mobile sluggish model, where it's a weaker notion of synchrony, where the messages can get delayed. And in this setting, we show that we can achieve the first permissionless protocol. And we also build the first expected O of 1 round Byzantine broadcast under strongly adaptive and corrupt majority setting. So this is going to be the outline for the rest of my talk. I'm going to introduce the preliminaries that are required to realize our construction. I'm going to tell you how we build our time lock puzzle. And then I'm going to explain how we can use this time lock puzzle in permissionless setting. So first, jumping into the preliminaries, the first building block which we need is homomorphic time lock puzzles. So homomorphic time lock puzzles are these nice primitives. Say you have time lock puzzles for message M1 and you have a time lock puzzle for message M2. These puzzles let you add these up together and come up with a new time lock puzzle, which is for the message M1 plus M2. And a solver has to spend time only opening this batched puzzle to get the values, the summation of these values out of it for the price of 1. They don't have to open M1 and M2 separately. The second key building block which we use is key homomorphic pseudorandom functions. Say a function f is a key homomorphic pseudorandom, then this has this nice property where if you take the PRF of message m under key k1, and if you add it with the PRF of message m under key k2, this is same as the PRF of message m under k1 plus k2. Yeah, so jumping into how our construction works. So in a traditional time lock puzzle, you'll be sending around group elements as a time lock puzzle. But in our setting, since we use IO, we send around obfuscated programs. So say in the setting, player I sends out an obfuscated program PI. So to tell you more about how this program works, first, this program takes in the size of the batch as an input. It has two key elements inside the circuit. So first one is, this is the message MI that the player I wants to put it in the time lock puzzle. That's hardwired inside the circuit. And also the key, the PRF key, which we use, that's also hardwired inside the circuit. So when someone runs this program with batch size n, it spits out two two outputs. The first one is it's going to spit out a time lock puzzle of the key ki, and it's going to give another vector, which is a structured vector of ciphertext. So what it's essentially going to do is it's going to take the PRF under the key ki for position 1. So we plug in value 1 and get the PRF value out of it, and we do this for all the positions in the vector. However, at position I, we also mask it with the value, the message that has to be encoded here. So that's going to be MI. So with this, this is how somebody generates a puzzle in our setting. So once you have these puzzles, so the question comes about how do you open up these puzzles in a batched manner? So so to do batch solving, so first the solver gets the program P1 to, in this example, there are three batch size is 3. The solver gets these programs. First, the solver runs the program P1, gets the two values out of it, K1 and the TLP of the key K1 and the masked ciphertext vector, does this for the player number 2, does this for player number 3, and so on. So you can see that the M1 is appropriately set in position 1, M2 is in position 2, M3 in position 3, and so on. So once the solver has computed these values, so using the homomorphic properties of the time lock puzzle, we can just sum up the time lock puzzles to get a new time lock puzzle, which is summation of the keys that were used in the individual time lock puzzles, and we call this K star. And the solver also sums up these individual vectors that was generated position wise, element wise. So you end up with summation of multiple PRF values plus message M1 at position 1, summation of PRF values under position 2 with message M2, and so on with message M3. Yeah, from now on, I'm going to focus only on the stuff which is on the rightmost corner. So I'm going to copy these values to the next slide. So in this slide, so first we exploit the homomorphic properties of the PRF. So essentially, when earlier this was a summation of PRF values, but the nice property about homomorphism lets us take the summation inside the PRF. So it's going to be a summation of keys rather than summation of PRF values. So we can do this for all the positions in the vector, and you end up with a vector that looks something like this on the left. So now we go about opening the time lock puzzle by spending time t. You open the time lock puzzle and you come up with the key K star. Once you have this key K star, so the solver runs the PRF under key K star and position I, position 2, position 1, position 2, and position 3, and so on, and then can come up with another vector as I show it here. So once you compute this vector, we can simply subtract it from the previous vector and get the message M1, M2, and M3. So that's how you recover the messages from the time lock puzzle. So jumping into how we use our time lock puzzles. So brief context. So in the permissionless setting, we do not know the number of nodes that are there in the system. And there is no authentication mechanism between nodes, and nodes have to communicate with each other over unauthenticated channels. So Nakamoto consensus was this breakthrough result where it was shown that you could do this, you can achieve permissionless consensus, and they used proof of work. And the key idea here is the longest chain always wins. That's the governing principle behind how Nakamoto consensus works. Prior works have shown that Nakamoto consensus is secure only in the synchronous model of communication. So just an overview of how it all ties together. So in the synchronous model of communication, you assume that all honest messages have an upper bound delta. So this is the time it takes for any honest message to get delivered to another honest person. And in synchronous model, you assume that every player knows the delta, and even the protocol designer knows the delta. But if you make such assumptions, you know that you can achieve permissionless consensus, which was considered to be a difficult problem in the past. However, the drawback of synchronous model is it's exceedingly optimistic. So we deploy Nakamoto consensus on the internet, but expecting you have synchronous communication is something that's exceedingly optimistic. Other models of communication are partially synchronous and asynchronous model of communication. So in this, we don't assume that there's a known delta for the honest messengers. And of course, when you assume that you can't do that, then there are impossibility results to say that you cannot achieve permissionless consensus by Elaine Shrew and Raphael Pass. But partially synchronous and asynchronous model capture the realities of the internet much closely than the synchronous network. So can we have the best of both worlds was the long lingering question. And Guo et al. And later by Abraham et al. Proposed this new model called a sluggish model of communication, where the honest parties are of two kinds. First one is the prompt one. Those nodes follow the protocol to the dot and also have synchronous communication. You also have another kind of honest node called sluggish node. These sluggish nodes follow the protocol, but for God knows they are suffering network jitters and a bunch of other network problems, but they are unable to satisfy synchrony. So the question which we ask in this work, can we achieve permissionless consensus in the presence of mobile sluggish faults? So one way to think about these models are through the power of the adversary. In the synchronous model, the adversary can read the messages but cannot stop them, but can at most delay them by delta. And partially synchronous or asynchrony, the adversary can read the messages, can delay them for a really, really long time. And the mobile sluggish model, you kind of have a mix of these two things. To give an overview of what we do in this work, so we modify Nakamoto consensus to achieve, using time lock puzzles, we modify it to achieve consensus in the mobile sluggish model. So the key idea here is we time lock encrypt any message someone sends in this network. So since the messages are time locked with the duration to be the synchrony value, the delta here. So the adversary is now forced to open the time lock to see what's inside the message. So that inherently forces the adversary either to deliver the message or take time to open it and see what's happening here. However, a key drawback in Nakamoto style protocols are there's only one person who is transmitting a message at any given time. So you need to have some sort of a decoy mechanism where even the non-block winners are creating enough message cover for someone who is the block winner so that the adversary doesn't know who is sending the block or who is sending a decoy. So in this case, the adversary is now forced to randomly pick its victims without knowing the contents. Long story short, we modify Nakamoto consensus in such a way that the adversary doesn't know what's inside a message, and it has to arbitrarily pick some messages to stop. And we use time lock puzzles that helps to get around the challenges posed by sluggish adversary. So to tell you more about decoys, so decoys are essentially a dummy time lock puzzle messages. It's going to give cover for the honest person who has just mined a block. However, as I said, in the permissionless setting, we don't know who is there in the system. So there is prone to Sybil attacks. So we, just like Nakamoto consensus, we use proof of work to get around this problem. So let's say that when you have a payload in Nakamoto consensus, you just compute the hash of it. And if it falls in some window 0 to D1, then you say that you have mined the block. That's how it goes about. So we just use the 2-for-1 trick, which was used in the past in fruit chains, Garay et al., and so on. So what we do is if the hash falls in another bucket D1 to D2, which is much easier than mining a block, but at the same time, it's not too easy enough where the adversary can flood the network. We say that if someone falls in this bucket, then it's going to, they have mined a decoy in this example, in this setting. So to give you a high-level overview of what and a simplified version of our protocol proceeds in two phases. The first phase is where you mine blocks or a decoy. If you're lucky, you stumble upon it. And of course, you first pick the longest chain. Then you time lock encrypt whatever you find, and you keep those messages with you right now. Then when you enter the solve phase, you multicast the puzzle you have. It could either be a decoy or a block, or if I was unlucky, I wouldn't have anything. But we set the parameters in such a way that with good probability you are able to mine at least one of the other. Then you multicast these time lock puzzles, and everybody receives these puzzles. They batch open using our time lock primitive, which I introduced in the previous section, and you extend the chain and you keep on doing this. So here is an example, a contrived example of how this happens. So in this example, these 4 miners are trying to add a third block to the blockchain. So what they do here is first, they enter the mine phase, they start a timer. Everybody tries to mine a decoy or block. In this example, except the third miner, everyone else is in luck, mines a decoy, but the third miner mines a block. So once they have their respective messages, they go about time lock encrypting it, whatever they have, and they wait for the mine phase to end. So now they get into the solve phase. So at the beginning of the solve phase, first thing you do is you send out all the messages you have. So in this case, A is sending its messages to everybody. In this thing, miner number 2 is sending it to others. In this case, miner 3 is doing it, and miner 4 is doing it. So at the end of the day, everybody should have had received those messages. And if the adversary would have stopped some message, you wouldn't have received it. But unfortunately, adversary cannot see what is inside the inside these time lock puzzles without spending time on it. So once you have these individual puzzles, you spend time, you bash them using our bashing property. So you can come up with a single puzzle, and you can spend time opening just the one puzzle you have and figure out who the winner of the puzzle is. So with this, you can find out who the winner is, and you can keep on doing this for other blocks in this manner. So in summary, we present a new time lock puzzle which has cool properties. Then we develop the first permissionless show the first permissionless protocol in the mobile sluggish model. And in the paper, we also show an attack on Nakamoto consensus in the mobile sluggish model. And another work which I didn't get to talk about was we show how to do, we build a generic compiler that can convert any weakly adaptive broadcast protocol into a strongly adaptive one. So here strong says that the adversary can look at the message, can delete any message from the network, even when it was sent by a node that was honest. So it's much harsher power of adversary. We build a compiler that can convert any weakly adaptive protocol into a strongly adaptive one, and we give the first expected round constant Byzantine broadcast on the strongly adaptive and majority corruptions. But the highlight of these broadcast works are you don't even have to use the TLP from our paper. You can use any batchable time lock puzzles to do it, and so you can in fact realize it in practice. Yeah, that's it. I'll stop and take questions. And I apologize for the animations. I'm not sure why it was just zooming out and off. Yeah.
Thanks. Questions? So can you say a little bit more about this generic compiler?
So this is in the we use a random oracle model. So essentially, it takes any message one sends in a weakly adaptive one. We put it in a time lock, and we send them around. The challenge is in how do you prove that this is in fact correct? And we show in the paper how to do it nicely. This is a long-standing open problem where you want to figure out how O of one around complexity.
That's in the sluggish model, right?
No, that's not in the sluggish model. So
Okay.
the 2 independent results. Yeah.
Okay.
Yeah.
Other questions? All right, I guess let's thank the speaker, and that's the end of the session.